Time moves differently when you're waiting for light that left a star 200 years ago. You can stand outside tonight and look up, and somewhere in that darkness, a supernova might have already happened. The explosion finished. The star collapsed or scattered. But the light hasn't reached you yet. It's still travelling, still crossing the gap between there and here. Welcome to the Sleepy Physicist. If this helps you rest, a like or subscribe helps others find this same quiet. Tonight we're thinking about distance not as emptiness, but as the thing that decides what survives. A supernova releases more energy in a few seconds than our sun will produce in its entire lifetime. The numbers are staggering. 10 to the 44 joules, enough to outshine an entire galaxy for weeks. And yet most of the universe doesn't notice. Most planets remain untouched. Most stars continue burning as if nothing happened at all. The question isn't really about the explosion, it's about the space in between. Space is not empty. We talk about it that way: vacuum, void, nothingness. But that's not quite right. There are atoms out there, not many. In interstellar space, you might find 1 hydrogen atom per cubic centimetre. In some regions, even less. 1 atom per cubic metre, per 10 cubic metres. It doesn't sound like much, it isn't much, but it's there. And when a supernova shockwave moves through space, it interacts with every single atom it encounters. Each collision transfers energy. Each interaction slows the wave just slightly. Over short distances, this doesn't matter. Over light years, it does. The shockwave leaves the dying star at 10,000 kilometers per second, sometimes faster. It's moving so quickly that material doesn't have time to flow, it just compresses. Atoms slam into each other, electrons get stripped away, the gas heats to millions of degrees. This is where the violence lives, right at the edge of the blast. But distance dilutes that violence in a way that feels almost intentional, though of course it isn't. Imagine a sphere expanding outward. At first, the sphere is small. All that energy is concentrated in a thin shell. But as the sphere grows, the surface area increases. The energy spreads across a larger and larger space. This is simple geometry, but the consequences are profound. Energy per unit area drops as 1 over radius squared. Double the distance, the intensity falls to 1/4. 10 times the distance, 1/100th the intensity. By the time the shockwave has travelled a few light years, it's no longer capable of vaporizing planets. It's still hot, still moving, but it's been stretched thin. Here's something people don't often consider. The supernova doesn't just send out a shockwave, it sends out light, radiation, particles, and these things all travel at different speeds. Light moves at light speed, obviously. The shockwave moves much slower, maybe 3% of light speed depending on the explosion. High-energy particles move somewhere in between, so a planet 10 light-years away doesn't experience the supernova all at once. First comes the light, a sudden brightening in the sky, then years later, the radiation. Then decades or even centuries later, the physical shockwave arrives. By the time the shockwave gets there, the star that exploded is ancient history. There's a term for this, the kill radius. It's the distance within which a supernova would strip away a planet's atmosphere, sterilize its surface, or otherwise render it uninhabitable. For a typical Type II supernova, that radius is somewhere between 25 and 50 light-years. Closer and you're in trouble. Farther and you're probably fine. Probably. Humans tend to think of danger as immediate. A predator, a cliff edge, something you can see and respond to. But cosmic danger doesn't work that way. It operates on timescales that make individual human lives irrelevant. A supernova's radiation could arrive at Earth tomorrow, and we wouldn't have been alive when the star exploded. The cause and the effect are separated by time in a way that makes causality feel strange, but we're not talking about Earth tonight. We're talking about the planets that do survive, the ones just outside the kill radius, the ones that experience the supernova but live through it. What does that look like? The first sign would be light. A new star appears in the sky, bright enough to cast shadows at night, brighter than the full moon, visible during the day even. It stays that way for weeks, maybe months. Then it fades, slowly at first, then faster. Within a year, it's gone. For a planet far enough away, that might be all that happens, just light. A strange temporary star. No destruction, no catastrophe, just a reminder that out there, something immense occurred. The radiation comes later, high-energy photons, X-rays, gamma rays. They hit the upper atmosphere and ionize molecules. Ozone layers get damaged. Atmospheric chemistry shifts. On Earth, scientists think a supernova within 50 light-years could cause noticeable ozone depletion. Not enough to end life, but enough to increase surface radiation. Enough to matter. But again, most of space isn't filled with planets. Most of space is exactly what it sounds like, space. And when a supernova wave expands into that emptiness, it simply continues. It doesn't destroy because there's nothing to destroy. It doesn't heat because there's nothing to heat. It just spreads, thins, fades. This is what stops a supernova from destroying everything nearby. Not a barrier, not a shield, just distance, just geometry, just the patient, indifferent dilution of energy across an expanding sphere. And time. Time helps too, because the farther the wave travels, the more time passes, and during that time the energy cools. The particles slow, the shock wave becomes less of a wall and more of a gust. Then a breeze, then a whisper. Eventually it becomes indistinguishable from the background noise of space itself. There are regions where this doesn't apply. Dense molecular clouds, stellar nurseries. Places where gas is thick enough that the shockwave doesn't dissipate. It compresses, it heats, it triggers new star formation. In those places, a supernova doesn't end things, it starts them. But those regions are rare. Most of space is like the space between stars in our own neighborhood. Sparse, quiet, patient, and in that sparseness, even the most violent events eventually lose their teeth. You could think of it as the universe protecting itself, but that would be giving it too much credit. It's not protection, it's just math, just physics, just the way things spread when there's room to spread. Still, there's something almost gentle about it. The way distance softens what would otherwise be unbearable. The star explodes in less time than it takes to blink, the core collapsing inward and rebounding outward in a cascade that begins and ends before human perception could register the start of it. And in that fraction of a second, two things are born: light and everything else. Light moves at exactly 299,792,458 meters per second in a vacuum, a speed that doesn't change, doesn't negotiate, doesn't care what it's leaving behind. And the moment the supernova's fireball reaches temperatures high enough to ionize matter completely, photons begin streaming outward in every direction at once. They don't wait for permission. They don't coordinate with the expanding shell of gas and plasma that will eventually follow. They simply leave, traveling through space the way light always does, unburdened by mass, unaffected by the violence that produced them. The shock wave, by contrast, is made of matter, atoms that have mass and therefore momentum and therefore inertia. And while they're moving incredibly fast by any terrestrial standard, 10,000, 15,000, sometimes 20,000 kilometers per second, they're still crawling compared to light, moving at perhaps 3% of light speed, maybe 5% in the most energetic explosions, which means that for every second that passes, the light pulls farther and farther ahead, opening a gap that grows wider with each moment. After 1 hour, the light has travelled over 1 billion kilometres, while the shockwave has barely crossed 100 million. And that difference isn't trivial. It's the difference between knowing and experiencing, between seeing the lightning and feeling the thunder, except stretched across distances so vast that the delay is not measured in seconds, but in years, decades, sometimes centuries. A planet 20 light years from the supernova sees the flash almost immediately. Well, immediately in cosmic terms, 20 years after the actual explosion, but at the speed information can travel. And for anyone watching that planet's sky, a new star appears, bright and sudden, outshining everything except perhaps the planet's own sun. And this is the warning, the announcement, the only signal that something catastrophic has occurred 200 trillion kilometers away. But the shockwave, the physical wall of superheated plasma carrying the star's scattered guts outward, that won't arrive for another 600 years, maybe 700, crawling through the space between stars at a pace that feels almost leisurely when stretched across such distances. Human beings don't think about information travelling separately from consequences, largely because in everyday life they arrive together or close enough to seem simultaneous. You see the ball before it hits you by only a fraction of a second. You hear the car horn and the car itself is already there. Cause and effect compressed into a single experienced moment. But in space on these scales, they separate completely, and you're left with knowledge suspended in time, awareness of danger that hasn't arrived yet, a kind of cosmic preview of disaster that may or may not matter by the time it reaches you. Consider what that means for a civilization. If such a thing existed on a planet in the path of a supernova's shockwave, they would see the explosion in their sky. They would have telescopes sensitive enough to measure the spectrum, determine the type, calculate the distance and therefore the arrival time of what's coming, and they would know with absolute certainty that in 600 years a wave of radiation and particle debris would sweep through their solar system. They would have 6 centuries to prepare, to leave, to build shielding, or simply to live out their lives, knowing their distant descendants would face something they themselves would never see. It's a strange kind of doom, one that arrives as information long before it arrives as experience. The light itself carries information, not just about the explosion, but encoded in its spectrum, the specific wavelengths absorbed and emitted, revealing which elements were present, how hot the fireball was, how fast the outer layers were moving. And scientists on Earth have used this method to study supernovae in distant galaxies, extracting entire narratives of stellar death from photons that travelled for millions of years to reach our instruments. The light is a messenger, accurate and precise, delivering news of events that finished long before human civilization existed. But light, for all its speed, doesn't carry force. Photons have momentum but no mass. They can push on things under the right circumstances. This is how solar sails work, how radiation pressure shapes comet tails. But they don't shatter planets, don't strip atmospheres, don't compress gas clouds into new star formation. They simply inform, illuminate, and pass through. The destruction, when it comes later. The shockwave carries mass, kinetic energy distributed across trillions upon trillions of atoms, each one moving at a fraction of light speed, but collectively representing an amount of energy that defies casual comprehension. And when this wall of matter encounters something, a planet, a gas cloud, a stellar wind from a nearby star, it doesn't pass through cleanly, it collides, transfers momentum, heats, compresses, disrupts. This is where the actual violence lives, not in the light but in the matter that follows it, delayed by the simple fact that matter cannot move as fast as light, bound by physics to arrive late. The gap between these two arrivals creates something almost like suspense. If the universe were capable of suspense, a waiting period where the evidence is visible but the consequences haven't manifested yet, and during this time, depending on the distance involved, entire processes can unfold. Planets can complete orbits. Ice ages can begin and end. Species can evolve. And then, finally, the shockwave arrives, and what was theoretical becomes real. There's a term in physics for this separation, the light travel time versus the shock travel time, and while it sounds clinical, it describes something profound about how the universe communicates with itself, how events propagate outward, not as unified phenomena, but as layered experiences. Light first, then radiation, then particles, then the shockwave itself, each moving at its own pace, each arriving on its own schedule. On human timescales, this feels absurd, almost fictional, but it's happening constantly throughout the galaxy. Supernovae exploding and sending their light ahead while the physical remnants lag behind, crawling through interstellar space at speeds that seem fast until you compare them to the one speed that nothing can exceed. And here's what's strange. The light doesn't care what it's announcing, it doesn't carry intent or warning. It's just electromagnetic radiation propagating through space according to the laws that govern all electromagnetic radiation. And yet it functions as a warning anyway, simply by arriving first, simply by being fast enough to outrun the destruction it represents. By the time you see the light, the decision has already been made. The shockwave is already in motion, already committed to its trajectory, and there's nothing that can stop it or redirect it or soften it beyond the natural dilution that distance provides. The light gives you time, but it doesn't give you options. It tells you what's coming without offering any way to prevent it. Unless, of course, you're far enough away that by the time the shockwave reaches you, it's dissipated into irrelevance, thinned and cooled, and spread across such a vast sphere that its passage is barely noticeable. A slight increase in cosmic ray flux, a faint disturbance in the interstellar medium, nothing more. In which case the light was never really a warning at all, just a notification, a distant headline about something that won't affect you, and you can watch the new star fade from your sky over the course of months and return to whatever you were doing before it appeared. The shockwave will still arrive centuries later, but you won't notice, and neither will anyone else. The star is gone, or rather the star as a unified object is gone. What remains is momentum and heat and gas moving outward at velocities that should mean escape, should mean freedom from the gravity well that held everything together for millions of years. But mass doesn't vanish just because it's no longer compressed into a sphere. The atoms are still there. The weight of them, the gravitational influence persists. Gravity doesn't care about temperature, doesn't care about velocity. It cares about mass, and mass alone. You can take a star, explode it into a shell of debris expanding at 10,000 kilometers per second, and the gravitational field surrounding that debris will be nearly identical to what it was before the explosion, at least at distances far enough away that the internal structure doesn't matter. A planet orbiting 10 astronomical units out wouldn't feel any immediate change in its orbit. The star exploded, yes. The light changed. The radiation increased. But the gravitational pull? Still there. Still pointing toward where the center of mass used to be. This seems wrong somehow. Explosion should break things, should release them. But gravity is geometry, not force in the way we usually think of force, and the geometry of space-time around a given mass doesn't reset just because that mass stopped being a star and became a cloud. At the core, though, at the very centre of what was once the star, something different happens. Most of the star's mass gets ejected. The outer layers, the hydrogen and helium envelopes, the fused elements from centuries of nucleosynthesis, all of that rushes outward and eventually dissipates into space. But the core itself, the innermost region where the collapse began, that doesn't always escape. Sometimes it stays behind, sometimes it compresses. In a Type II supernova, the kind that happens when a massive star runs out of fusion fuel, the core collapses inward while the outer layers explode outward, and what's left at the centre depends entirely on how much mass falls inward during those first few seconds. If it's between about 1.4 and 3 solar masses, you get a neutron star. More than that, and it collapses further into a black hole. Less than that, and you might get nothing at all, just a dispersing cloud with no central remnant. But when a neutron star forms, gravity wins in a way that's almost absolute. Neutron stars are small, absurdly small for the amount of mass they contain, roughly 20 kilometers across. You could drive around one in an afternoon if there were roads and if the gravity didn't crush you into a layer of atoms 1 Fermi thick. The density is incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravitational field at the surface is so intense that light itself bends noticeably, and time runs slower there than it does in empty space far away. This object, this remnant, sits at the centre of the expanding debris cloud and holds on. Not to everything. The outer layers are gone, moving too fast, too far already beyond the point where gravity can pull them back. But the remnant still exerts influence, still pulls. The debris cloud might be expanding, but it's not expanding uniformly. Some regions move faster than others, some regions are denser, and wherever there's density, there's gravity, and wherever there's gravity, there's curvature, and wherever there's curvature, motion changes. The debris doesn't fly outward in straight lines, it curves, bends, some of it even falls back. Human beings observing supernova remnants from Earth often see asymmetric structures, loops, filaments, regions where material seems to have reversed direction and collapsed back toward the centre. This isn't random, it's gravity. The remnant pulling on the inner edges of the debris field, slowing them, redirecting them, sometimes capturing them entirely. Over thousands of years, some of the ejected material accretes back onto the neutron star. Not much, a tiny fraction of what was originally expelled, but enough to matter, enough to add mass, enough to spin the neutron star faster or heat its surface or create brief flares of X-rays as infalling material crashes down at relativistic speeds. And if the neutron star has a companion, another star orbiting nearby, something that survived the explosion, it can pull material from that companion's outer atmosphere, slowly feeding, growing denser, spinning faster, until eventually it might collapse further into a black hole or explode again in a different kind of event entirely. Gravity doesn't forget, doesn't release. Even the debris that escapes, that moves outward into interstellar space and never returns, still feels the pull. Faint, negligible at large distances, but present, always present. The gravitational field of a dispersed cloud is weak compared to the field of a star. But it's not zero. Matter still attracts matter. Dense clumps within the debris field pull on each other, slowly coalescing over millennia into smaller structures, fragments that might one day collapse into new stars or planets, or simply drift as cold, dark masses too small to ignite. This is part of why supernova remnants don't just vanish. They linger. They evolve. They remain gravitationally bound to their own history in ways that complicate the simple narrative of explosion and dispersal. There's also this. The debris field itself has angular momentum. Stars rotate, slowly usually, but they rotate. When the core collapses, conservation of angular momentum means the rotation speeds up dramatically. This is why neutron stars spin so fast, some completing hundreds of rotations per second. But the outer layers, the ones that explode outward, they carry angular momentum too. They don't just expand spherically, they spiral, twist. And this rotation creates structure within the debris cloud, regions where material bunches up, where gravity concentrates, where secondary collapse becomes possible. Over tens of thousands of years, a supernova remnant can begin to look less like an explosion and more like a slowly churning nebula, still expanding but also condensing in places, still hot but cooling, still luminous but fading. Gravity shapes this evolution. Not dramatically, not obviously, but constantly. You can't stop gravity, you can only delay it. The debris moves outward, yes, but it's fighting gravity the entire time. Slowing, not much. Not enough to reverse direction entirely in most cases, but slowing. Every atom of gas in that expanding shell is still gravitationally bound, however weakly, to every other atom, and over enough time that binding matters. In the end, what stops a supernova from destroying everything nearby isn't just distance or time or the dilution of energy across space. It's also this. The explosion never fully escapes itself. Part of it stays behind, part of it pulls inward, part of it remembers what it used to be, and that memory, written in the curvature of space-time around a neutron star or a dispersing cloud, persists long after the light has faded and the shockwave has passed. Gravity doesn't let go, it just waits. You're watching the debris field expand. Hours after the explosion, it's already light minutes across. Days later, light hours. The gas is hot enough to ionize completely. Every atom has been stripped down to nuclei and free electrons. The temperature sits somewhere near 10 million Kelvin. The shockwave front moves outward at 15,000 kilometers per second, maybe more depending on the energy of the explosion. And then something begins to happen that you wouldn't expect from simple momentum. The expansion slows down, not dramatically, not suddenly, but measurably. Over weeks, over months, the velocity at the leading edge of the debris shell decreases. Not because it's hitting anything solid, not because gravity is pulling it back with enough force to matter yet. It slows because the debris itself creates resistance. The interstellar medium isn't empty. You already know this from earlier. 1 atom per cubic centimeter in most places, sometimes more, sometimes less. But it's there. And when the supernova shockwave plows into this sparse gas, it sweeps it up, collects it. The leading edge of the debris shell accumulates interstellar material like snow building up on a plow blade. This changes things. At first, the mass of the swept-up material is negligible compared to the mass of the debris shell itself. A few solar masses of ejected star hitting a wisp of hydrogen doesn't slow down, but the debris shell is expanding, its surface area is growing. The volume of space it sweeps through every second increases as the square of the radius. More volume means more interstellar gas encountered. More gas means more mass added to the leading edge. And momentum, you remember, is conserved. If you add mass to a moving object without adding energy, the velocity has to drop. This is basic physics. The total momentum stays the same, but it gets distributed across more and more mass. So the debris shell, despite carrying enormous kinetic energy, begins to decelerate. Slowly at first. A few kilometers per second lost over decades. Then more still. By the time a supernova remnant is 1,000 years old, the shockwave might be moving at a few thousand kilometers per second instead of 15,000. By 10,000 years, it might be down to a few hundred. The expansion doesn't stop, but it loses its edge, loses its violence. The wave that could have vaporized planets becomes something gentler. But there's another process happening at the same time, something less obvious. The debris shell isn't just moving outward, it's also radiating, cooling. When atoms collide at these speeds, they emit light. Mostly X-rays at first because the gas is so hot, then ultraviolet as it cools, then visible light, then infrared. Every photon that escapes carries energy away from the system. Energy that used to be kinetic, energy that used to push the debris outward. This is radiative cooling, and it works like a brake. You can think of it as the shell glowing itself to a stop, not a complete stop. The debris will keep expanding for hundreds of thousands of years, but the rate of expansion decreases not just because of swept-up mass, but because the shell is actively losing energy to space in the form of light. Human astronomers observe this. They point telescopes at old supernova remnants and measure the spectra. The emission lines tell them what elements are present, how fast they're moving, how hot they are. And what they see consistently is that older remnants are cooler and slower than younger ones. The Crab Nebula, about 1,000 years old, still has filaments moving at several thousand kilometers per second. The Vela remnant, about 11,000 years old, has slowed to a few hundred. Sedov-Taylor phase, they call it, named after the physicists who first worked out the mathematics. The details are complex, but the principle is simple. The shell expands into the interstellar medium. It sweeps up mass. It radiates energy. And because of these two processes, it slows down. But here's what makes it strange. The shell is slowing itself down, not hitting a wall, not being stopped by some external force. It's the interaction between the debris and the medium it's moving through that creates the resistance. The debris encounters hydrogen, sweeps it up, heats it, which causes it to radiate, which cools the debris, which allows the hydrogen to remain dense enough to slow things further. It's a feedback loop. The faster the shell moves, the more violently it interacts with the interstellar medium. The more energy it radiates, the more it slows down. Until eventually, thousands of years later, the distinction between supernova debris and interstellar medium becomes blurry. The shell has mixed with its surroundings. The shockwave has dissipated. What remains is just a slightly denser, slightly warmer patch of space where a star used to be. You might wonder if this means the debris eventually stops completely. It doesn't. Not in any finite time. The expansion continues, but it becomes indistinguishable from the general turbulent motion of gas in the galaxy. The supernova remnant merges into the background, becomes part of the medium it was once racing through, and during this entire process, the debris shell itself is not uniform. It's clumpy, unstable. Regions where the density is slightly higher collapse inward, while regions of lower density expand faster. Instabilities grow. The smooth shell you might imagine breaks apart into filaments, fingers, bubbles. The Rayleigh-Taylor instability, the Kelvin-Helmholtz instability, names for the ways fluids behave when they're accelerated or sheared. Humans sometimes forget that supernova debris acts like a fluid. It's so hot and so diffuse that individual atoms don't matter. Only the collective behavior matters, and fluids, when pushed hard enough, develop structure. They don't stay smooth. They break into eddies and currents and streams. So the shell that's slowing itself down is also fragmenting itself, breaking apart into smaller structures that each slow down at different rates depending on their density and their interaction with the surrounding medium. By the time 10,000 years have passed, the shell isn't really a shell anymore. It's a network of glowing filaments embedded in a larger bubble of hot, thin gas. still expanding, still cooling, still slowing. And all of this happens because the debris can't move through space without interacting with what's already there, can't expand without sweeping up mass, can't stay hot without radiating. The explosion sends everything outward with tremendous force, yes, but the universe has its own subtle ways of absorbing that force, not through barriers but through accumulation, through the slow, patient work of friction distributed across light years. The shell slows itself because it can't help but touch the medium it's travelling through, and every touch takes something away, a little momentum, a little energy, a little speed, until what was once violent becomes merely fast, and then merely moving, and then, eventually, part of the quiet drift of gas between stars. Before the star exploded, before the core collapsed, and the outer layers tore themselves apart in a cascade of shock and heat, there were magnetic fields threading through the star's interior, weak by most standards but persistent, woven into the plasma over millions of years of rotation and convection, and the slow churning that happens inside any massive object made of ionized gas. These fields don't vanish when the star dies. They stretch, they amplify, they guide. Magnetic fields in space are not like the fields around a bar magnet on a table, with iron filings arranging themselves in neat arcs from pole to pole, because there is no table, no gravity to settle things into visible patterns, and the fields themselves are often so weak that only their effects on charged particles reveal their presence at all. But weak does not mean irrelevant. In the context of a supernova, where every atom is ionized and moving at thousands of kilometers per second, even a faint magnetic field becomes a structure that matter must respond to. Charged particles cannot move freely across magnetic field lines. They spiral around them instead. This is called gyration, and it happens because the magnetic force acts perpendicular to a particle's velocity, bending its trajectory into a helix that wraps around the field line like thread around an invisible string. And while an individual particle's motion might seem chaotic, the collective behavior of trillions of particles all spiraling around the same field lines creates flow patterns that look organized, deliberate, even though no intelligence designed them. The supernova debris carries the star's magnetic field outward with it, frozen into the expanding plasma in a way that physicists describe as the field being frozen in, which is not a metaphor but a description of how ionized gas and magnetic fields become coupled in conditions where electrical conductivity is extremely high. The field lines move with the gas moves with the field lines. They are bound together, inseparable. And so when the debris expands, the magnetic field expands too, stretching outward but not disappearing, not dissipating in the way you might expect. And in fact, in some regions the field strengthens as the plasma compresses. The explosion is not spherically symmetric. It cannot be. Stars rotate, and that rotation persists in the debris, creating angular momentum that skews the expansion into an oblate shape, flattened at the poles, bulging at the equator, and the magnetic field reinforces this asymmetry, channeling plasma along certain directions while resisting flow in others. Near the magnetic poles of the original star, the field lines are tightly packed, strong enough to funnel material into narrow jets that shoot outward faster than the rest of the debris. And these jets can extend for light years, carrying gas at higher velocities than the main shell, creating structures that astronomers observe and call bipolar outflows, though the term sounds more clinical than the reality, which is a star's guts being squeezed along invisible rails into space. There are supernova remnants where this structure is visible even now, thousands of years after the explosion. The Crab Nebula has a pulsar at its centre, a neutron star spinning 30 times per second, and its magnetic field threads through the surrounding debris in patterns that glow when high-energy electrons spiral along them and emits synchrotron radiation, and the result is a nebula that looks nothing like a sphere but instead resembles something porous, threaded, as though the explosion were combed into alignment by forces no one can see directly, but everyone can infer from the shapes left behind. Magnetic fields also trap particles, especially the most energetic ones. The electrons and protons accelerated to near light speed by the shockwave itself, and these particles cannot escape easily because every time they try to move outward across a field line, they get bent back, forced to spiral, and so they remain trapped within the expanding shell, bouncing back and forth between the inner and outer edges in a process called diffusive shock acceleration, which is how cosmic rays are born. The particles gain energy each time they cross the shock front. They bounce, they accelerate, they bounce again. Eventually some of them escape, shooting off into interstellar space as high-energy radiation, but many remained confined within the magnetic structure of the remnant for centuries. This confinement is not a barrier in the physical sense, not a wall, but rather a topology, a shape that charged particles find difficult to leave because every path outward curves back inward, and so the magnetic field becomes a kind of cage made not of bars but of geometry, and the debris itself remains partially trapped within this geometry even as it expands, slowed not just by mass and radiation but by the invisible architecture of the field itself. And then there is the interstellar magnetic field, the field that exists between stars, weak and tangled, only a few microgauss in strength, barely enough to deflect cosmic rays, but present, always present. And when the supernova debris expands into this background field, it does not simply plough through, but instead compresses it, amplifies it, and the compressed interstellar field pushes back, creating pressure that slows the expansion in certain directions while allowing it to continue more freely in others. The result is that supernova remnants often look elongated, stretched along the direction of the ambient magnetic field. And this elongation is not random, it is not decorative. It is the record of an interaction between the explosion's internal field and the galaxy's external field. Two structures that cannot ignore each other because they are both woven into the same plasma, the same charged particles, the same space. Humans looking at these remnants sometimes describe them as beautiful, and they are, but the beauty is accidental, a byproduct of physics rather than design, the way frost forms patterns on a window. Not because the water wants to make art, but because the crystallization follows rules, follows gradients, follows the paths of least resistance and greatest symmetry. Magnetic fields create beauty in the same way, not intentionally, just inevitably. In some cases, the magnetic field creates shells within shells, nested structures where the debris has been slowed and compressed into layers separated by regions of lower density. And these layers persist for thousands of years, visible as rings when viewed from the right angle, and each ring represents a moment when the expansion hit a magnetic obstacle, slowed, compressed, then continued onward, leaving a record behind like growth rings in a tree. Except the tree is made of ionized gas moving at 1,000 kilometers per second. The field does not stop the explosion. It redirects it, shapes it, gives it structure, and in doing so it changes where the debris goes, which regions of space get enriched with heavy elements, which molecular clouds get compressed into star formation, which parts of the galaxy receive the shock and which parts are spared. Magnetic fields, invisible and ancient, decide where the consequences land. They bend the explosion without ever being seen, and when the remnant finally fades, when the gas has cooled and mixed with the interstellar medium and the distinction between debris and background has blurred into nothing, the magnetic field remains, slightly stronger than it was before, slightly more tangled, woven with iron and oxygen and silicon from a star that no longer exists. The field remembers even when everything else has dispersed. There are regions in space where matter exists in such sparse concentrations that calling it a vacuum feels almost generous. Not true vacuum, nothing is ever truly empty, not even in the coldest voids between galaxy clusters, but sparse enough that a cubic meter might contain only a few atoms. Hydrogen mostly, sometimes helium, occasionally a stray carbon nucleus or an oxygen ion, remnants from older stellar winds or previous supernova that have long since dispersed. The supernova wave reaches these regions eventually. It travels outward for decades, centuries, pushing through denser pockets of interstellar medium, sweeping up gas, slowing as it accumulates mass and radiates energy. But eventually it crosses into zones where there is almost nothing to sweep. The density drops. The wave continues, but it encounters fewer and fewer particles with each passing year. Collisions become rare. A shockwave requires matter to be a shockwave. It needs something to compress, something to heat, something to push against. Without that, the concept starts to lose meaning. The wave doesn't disappear, the energy is still there, the momentum still exists. But the physical manifestation of that energy changes. Instead of a dense shell of hot gas slamming into surrounding material, it becomes something more diffuse, a pressure gradient, a thermal disturbance, a slight increase in the kinetic energy of atoms that were already moving through space on their own trajectories. The temperature of the shockwave front drops. Not because the energy vanishes, but because temperature is a measure of average kinetic energy per particle. And when there are fewer particles, the energy per particle can remain high, while the bulk temperature, the thing you would measure if you could place a thermometer there, falls. The wave still moves at hundreds or thousands of kilometers per second, but the sensation of heat, if anything could sense it, diminishes. Pressure also drops. Pressure requires collisions, particles bouncing off surfaces or off each other, exerting force. In near emptiness, collisions happen so infrequently that pressure becomes negligible. The wave exerts almost no force. A planet in its path would feel nothing, not because the wave has stopped, but because there aren't enough particles striking the planet's atmosphere to transfer meaningful momentum. This is different from earlier stages of the expansion, where the wave could strip atmospheres, ionize gases, trigger auroras visible from orbit. Out here in the low-density regions, the wave passes and leaves almost no trace. Light, however, still propagates. The few atoms that do get excited by the passing wave emit photons as they return to lower energy states. These photons travel outward, carrying information about the encounter. But the emission is faint, so faint that only the most sensitive instruments could detect it. The wave becomes invisible, not because it's gone, but because there's nothing left to make it glow. Think of it like sound moving through air versus sound trying to move through near vacuum. In air, sound is a pressure wave, compressions and rarefactions that propagate because molecules collide and transfer energy. In near vacuum, there aren't enough molecules to sustain that kind of wave. Individual molecules might carry kinetic energy from the source, but they don't form a coherent wavefront. The wave dissipates into isolated particles, each moving on its own, no longer connected by frequent collisions. The supernova shockwave does something similar in these low-density regions. It fragments, stops behaving like a unified front, becomes a distribution of high-velocity particles moving outward, mostly in the same direction, but no longer compressed into a shell. Humans studying supernova remnants have observed this transition. Young remnants in dense regions glow brightly in X-rays and optical wavelengths. Old remnants in sparse regions fade, their emission dropping below detectable levels long before the kinetic energy actually dissipates. The energy is still there, distributed among particles that have simply stopped colliding often enough to produce light. This raises a question. If a shockwave passes through a region and nothing records its passage, did it have an effect? Technically, yes. Every atom encountered gains a small amount of kinetic energy. Every magnetic field line gets slightly perturbed. Every photon emitted carries information into the universe that wasn't there before. But practically, functionally, the answer is closer to no. The region remains essentially unchanged. No structures form, no chemistry gets disrupted, no molecules break apart. The wave moves through like wind through a room with no curtains, no papers, nothing to flutter or shift. There's something almost peaceful about this. The most violent event a star can undergo, spreading outward for thousands of years, finally reaching a place where it can't hurt anything because there's nothing there to hurt. The violence exhausts itself not by hitting a wall, but by running out of medium to propagate through. Energy, of course, doesn't disappear. It never does. The kinetic energy of the debris remains, carried by individual atoms that continue moving outward at high velocities. But the collective behavior, the shock wave, the front, the wall of compressed gas, dissolves. The atoms become part of the background, indistinguishable from the general population of particles drifting through interstellar space. In some ways, this is how supernovae end. Not with a final collision, not with a boundary where the expansion stops, but with a gradual fading into irrelevance, a dispersal so complete that the distinction between supernova debris and ordinary interstellar medium becomes arbitrary. Planets orbiting stars in these low-density regions would see the supernova light years earlier, the brightening sky, the new star appearing and then fading over months. They would never feel the shockwave, never experience the radiation bombardment, never have to calculate safe distances or worry about atmospheric loss. The light arrives, delivers its information, and departs. The shockwave arrives much later and does nothing. This is protection by absence, not a shield, not distance alone, but the simple fact that there is nothing nearby for the wave to interact with. The energy passes through empty space, and empty space absorbs it without flinching, without recording, without responding in any measurable way. And eventually, after enough time has passed and enough space has been crossed, even the debris itself cools, slows, settles into equilibrium with its surroundings. The atoms that were once part of a star become indistinguishable from atoms that were never part of a star. They drift, they wait. They might eventually join a molecular cloud, condense into a new star, fuse into heavier elements, explode again. But in the meantime, out here in the near emptiness, they simply move, without collision, without consequence, silent. The wave arrives at a molecular cloud that has existed for 3 million years. The cloud is cold, 10 Kelvin in most places, 20 in the denser cores where hydrogen molecules cluster together, shielded from starlight by layers of dust grains, complex aggregates of carbon, silicon, oxygen, iron, frozen water ice coating their surfaces like frost on stones. The density here is high by interstellar standards. 1,000 molecules per cubic centimetre, in some pockets 10,000, enough that gravity has already begun pulling material inward in places, preparing the slow collapse that might someday form stars. The supernova shockwave has been travelling for 2,000 years. It has crossed 40 light-years, swept up interstellar hydrogen, cooled from millions of Kelvin to hundreds of thousands, slowed from 15,000 kilometres per second to 3,000. Still fast, still hot, but no longer capable of vaporizing solid matter on contact. When the wave reaches the edge of the molecular cloud, something changes. The cloud is not passive. It has mass. It has density. The shockwave encounters resistance, real resistance, not the sparse scattering of atoms in open space, but a coherent structure with enough matter to push back. The leading edge of the wave compresses the cloud's outer layers. Density increases. Temperature rises. The cold hydrogen begins to heat. This is not destruction. This is transformation. In the thinnest regions, the shockwave passes through and leaves the gas ionized but intact. Hydrogen atoms lose their electrons. The cloud glows in ultraviolet for centuries, then slowly recombines as the wave moves on. But in the denser regions where molecular hydrogen dominates and dust grains have already begun coagulating, the compression triggers something different. Gravitational collapse accelerates. The cloud was already collapsing in places, dense cores pulling inward under their own mass, a process that typically takes millions of years. The shockwave arrives and compresses these cores further, increasing their density faster than gravity alone could manage. Material that would have taken another million years to collapse condenses in 10,000 years instead. Cores that were marginally stable become unstable. Fragments that might have dispersed now hold together. Stars begin to form, not immediately, not in the way a fire ignites, but the seeds are planted. Regions of the cloud that were too diffuse to collapse on their own now have enough density. Regions that were collapsing slowly now collapse quickly. The shockwave acts as a catalyst, not by adding material but by rearranging what was already there, compressing, organizing, pushing the cloud across thresholds it might never have crossed otherwise. Human astronomers have observed this in nearby star-forming regions. The edges of supernova remnants show bright clusters of young stars, stars that formed in the last few million years, which is recent on cosmic timescales. The correlation is clear: supernovae trigger star formation. Not always, not everywhere, but often enough that the process seems fundamental. The mechanism is straightforward. Compression increases density. Increased density strengthens gravity. Stronger gravity pulls material inward faster. The cloud fragments into smaller clumps. Each clump contracts. Temperature in the core rises as gravitational potential energy converts to heat. Eventually, if the clump is massive enough, the core reaches 10 million Kelvin and hydrogen fusion begins. A star ignites. The supernova's energy, which left the dying star 2,000 years ago, now powers the birth of something new. But not all of the cloud forms stars. Much of it remains diffuse, heated, but not compressed enough to collapse. This heated gas expands, pushed outward by thermal pressure, and some of it escapes the cloud entirely, blown into surrounding space by the force of the shockwave. The cloud loses mass, shrinks. The remaining dense cores become more isolated, less likely to merge, more likely to form individual stars rather than massive clusters. The shockwave sculpts the cloud, carves it, removes the loose material and leaves behind only the densest knots, the regions where gravity can still hold on despite the violence passing through. There are clouds where multiple supernovae have passed through over time. Each wave compresses, each wave heats, each wave triggers a new generation of star formation. The result is a layered structure, young stars near the most recent shockwave front, older stars deeper in the cloud's interior and in between, regions where gas has been pushed aside, creating cavities, bubbles, spaces where nothing remains but thin ionized hydrogen, glowing faintly in the dark. Some of these bubbles are light years across. The Orion Nebula has them, the Eagle Nebula, the Carina Nebula. Every major star-forming region shows evidence of shockwaves passing through, compressing gas, triggering collapse, creating the conditions for new stars while simultaneously destroying the very clouds those stars are born from. It's paradoxical. The supernova both creates and destroys. It ends one star's life and begins dozens of others. The debris spreads outward, carrying heavy elements, carbon, oxygen, silicon, iron, that will eventually become part of the new stars, part of their planets, part of whatever chemistry develops in those systems. The atoms that once fused in the core of the dying star now drift through space, cool, condense onto dust grains, get incorporated into molecular clouds, collapse into protostars, heat up again, fuse again. The cycle continues. Not perfectly, not identically. Each generation of stars has more heavy elements than the last. The universe ages. Chemistry becomes more complex. Dust grains grow larger. Planets form more easily. But the mechanism remains the same. Stars die. Clouds compress. Stars form. Stars die. The molecular cloud doesn't know it's being shaped. It has no awareness of the shockwave approaching. It simply responds to pressure, to heat, to density changes the way any gas would respond. Compress it and it heats. Heat it enough and it ionizes. Compress it while it's cold and it collapses. Physics, not intention. And yet the result looks almost deliberate. The cloud fragments into stars arranged in patterns that suggest design. Clusters, filaments, arcs. The shockwave passes through and leaves behind something that resembles architecture, though no architect planned it. Humans looking at images of star-forming regions often describe them as nurseries, and the term fits. Stars are born here. But the nursery exists only because something died nearby, and the death was violent enough to reshape the surrounding environment, to compress old gas into new stars, to turn remnants into beginnings. The nebulae that were already there don't disappear when the supernova arrives. They change, they glow, they collapse in new places. They lose some mass and condense the rest. They become something different without ceasing to be themselves. And in 10 million years, some of those new stars will explode. Their shock waves will reach other clouds. Those clouds will compress. More stars will form. The process feeds itself, not infinitely. Eventually the galaxy will run out of gas, the clouds will disperse, star formation will slow and then stop, but that's billions of years away. For now, the clouds are full, the shockwaves keep coming, the stars keep forming. The nebulae were already there. They've been there for millions of years. And they'll be there for millions more, reshaped by each passing wave, glowing in the dark, slowly turning themselves into stars. Think about a bullet passing through water. If the bullet moves slowly enough, the water has time to flow around it. Molecules shift, pressure distributes. The bullet pushes water aside and the water fills in behind it. Resistance is high. The bullet loses energy quickly. But if the bullet moves extremely fast, faster than the water molecules can respond, it punches through before the surrounding liquid can react. The hole forms, yes, but the disturbance is localized, minimal. The bullet is gone before the water knows it was there. Supernova debris behaves similarly when it moves through certain regions of space. You have particles, iron nuclei, oxygen ions, silicon atoms, traveling at 3,000 kilometers per second. Some fragments move even faster, 10,000 kilometers per second. A few high-energy outliers might reach 30,000. These are not slow objects. At these speeds, the time it takes for a particle to cross a region of space becomes shorter than the time it takes for that region to respond. Atoms have interaction cross-sections. This is the effective area over which they can collide with other atoms. For hydrogen, the cross-section is roughly the size of the electron cloud, about an angstrom. When two hydrogen atoms approach each other, their electron clouds repel. They don't have to physically touch. The electromagnetic force pushes them apart before contact. But this repulsion takes time, not much time. The electromagnetic interaction propagates at the speed of light. But it still takes time for the fields to propagate, for momentum to transfer, for trajectories to change. If a particle is moving fast enough, it crosses the interaction zone before the repulsion has fully taken effect. The atoms still interact, but not completely, not efficiently. The collision is glancing rather than head-on. Energy transfers, but only partially. Imagine a supernova particle entering a molecular cloud. The cloud has density, 1,000 molecules per cubic centimetre. Under normal circumstances, the particle would collide with these molecules, heat them, ionize them, transfer its kinetic energy and slow down. But if the particle is moving at 10,000 kilometers per second, the time it spends near any given molecule is on the order of picoseconds, a trillionth of a second. During that time, the electromagnetic fields interact, electrons respond, but the nuclei, heavier, slower to accelerate, barely move. The particle passes through and the molecule is left vibrating, slightly warmer, possibly ionized but not destroyed. Not shattered. The interaction happened, but incompletely. This is why some supernova debris travels farther than you'd expect based on the density of the medium it's moving through. It's moving too fast to be stopped efficiently. The medium can't absorb the energy quickly enough. The debris punches through. You see this in cosmic rays. These are particles accelerated to near light speed by supernova shockwaves. They travel across the galaxy, sometimes across intergalactic space, encountering dust, gas, magnetic fields, and yet they continue. They lose energy slowly, through rare collisions and interactions with photons, but they don't stop. They're too fast. Their interaction time with any obstacle is too brief for the obstacle to capture them. There's a threshold. Below a certain velocity, particles collide normally. Energy transfers efficiently, the particle slows. Above that threshold, collisions become inefficient. The particle grazes rather than strikes. It maintains most of its momentum. For hydrogen colliding with hydrogen, that threshold is somewhere around a few hundred kilometers per second, depending on the temperature and ionization state of the medium. Below that, collisions are thermal. Above that, collisions become ballistic. The particles don't thermalize, they don't reach equilibrium with their surroundings, they pass through as outsiders. Supernova debris moves well above this threshold. So when the debris encounters a planet, for instance, the fastest moving particles, those in the extreme tail of the velocity distribution, don't deposit much energy in the atmosphere. They hit the upper layers, ionize a few molecules and continue through. They might pass entirely through the planet if it's small enough, exiting the other side still travelling at thousands of kilometers per second. The slower particles, those moving at a few hundred kilometers per second, deposit more energy. They collide more efficiently, they heat the atmosphere, they cause damage. But even these particles don't stick around, they hit and move on. The interaction is brief. This creates a strange situation where the most energetic particles cause the least damage per particle. They carry enormous energy, yes, but they don't stay long enough to transfer it. They are like punches that are so fast they don't land fully. The fist passes through before the force can accumulate. You might think faster means more dangerous, and in some contexts it does. A faster particle carries more kinetic energy, but kinetic energy alone doesn't determine damage. What matters is how much of that energy gets deposited, and deposition requires time, requires interaction, requires the projectile to slow down inside the target. A particle moving at 1% of light speed doesn't slow down inside a planetary atmosphere. It barely notices the atmosphere is there. It enters, ionizes a column of air along its path, and exits. Total energy deposited, a fraction of what a slower, heavier particle would leave behind. Astronomers measuring the effects of supernovae on nearby planets have to account for this. The velocity distribution of the debris matters. The slowest particles cause atmospheric heating and loss. The fastest particles contribute to cosmic ray flux but don't directly strip atmospheres. They are gone too quickly. There are regions of space filled with high-velocity debris from ancient supernovae. Particles that have been travelling for millions of years, still moving at thousands of kilometres per second, occasionally passing through molecular clouds or planetary systems and leaving almost no trace. They interact, yes, they collide, but the collisions are so brief, so glancing, that they might as well not have happened. Speed protects them. Or more accurately, speed reduces their ability to interact, which in turn protects whatever they're passing through from their energy. This is the paradox. The supernova is violent, the energy is real. But if the debris moves fast enough, most of that energy never gets transferred to the surrounding medium. It stays locked in the motion of the particles themselves, carried outward until the particles finally slow down through accumulated small interactions over light years, or until they escape the galaxy entirely and drift into intergalactic space, where nothing will slow them for billions of years. Too fast to matter. Not because the energy doesn't exist, but because there's no time to transfer it, no time to stop, no time to collide properly. The debris passes through, and the region it passed through remains largely unchanged, marked only by a faint ionization trail that fades within hours, a memory so brief it barely qualifies as a memory at all. The first photons leave the moment the core rebounds. The collapse happens in less than a second. The rebound is just as fast. The outer layers of the star, falling inward at a significant fraction of light speed, suddenly hit an incompressible neutron core and bounce. The kinetic energy of that impact converts to heat. Temperatures spike to hundreds of billions of Kelvin. At those temperatures, photons created are not visible light, not even ultraviolet. They are gamma rays. Gamma rays carry millions of electron volts of energy. Each photon is capable of ionizing atoms, breaking molecular bonds, disrupting cellular chemistry if such chemistry existed nearby. But the gamma rays don't travel in straight lines out of the star. They scatter. The material around the core is dense, opaque, and every photon collides with electrons, gets absorbed, re-emitted at slightly lower energy, absorbed again. This process repeats millions of times. The gamma rays diffuse outward through the star's outer layers, gradually losing energy with each interaction, their wavelengths shifting from gamma to X-ray to ultraviolet. By the time they reach the surface of the expanding debris shell and finally escape into space, days have passed. The initial gamma burst has been absorbed, thermalized, converted into a broader spectrum. What emerges is still intense. X-rays dominate, ultraviolet follows, some visible light. But the hardest, most penetrating radiation never makes it out. It deposits its energy inside the debris itself, heating it, driving the expansion. The X-rays that do escape spread outward at light speed. You stand on a planet 20 light-years away. You don't know the supernova has happened yet. The star looks normal in your sky. Then 20 years after the core collapsed, the light arrives. First comes the visible brightening. The star becomes intensely bright, brighter than anything else in the night sky. Then, nearly simultaneously, the X-rays arrive, but they've already weakened. Radiation follows an inverse square law. The intensity drops as 1 over distance squared. 20 light-years is about 1.9 times 10 to the 14th kilometers. The X-rays that left the supernova spread out over a sphere with that radius. The surface area of that sphere is immense. The energy flux, The amount of energy hitting each square meter is the total energy divided by the surface area. By the time the X-rays reach your planet, the flux has dropped by a factor of roughly 10 to the 28 compared to what it was at the surface of the supernova. The radiation is still there, still detectable, but vastly weakened. The X-rays that could have sterilized a planet at 1 light-year are now barely strong enough to ionize the upper atmosphere at 20 light-years. Your planet's atmosphere absorbs most of them. Oxygen and nitrogen molecules in the thermosphere interact with the X-rays, absorbing their energy, breaking apart into ions and free electrons. The atmosphere heats, glows faintly in ultraviolet, but the surface below remains unaffected. The radiation doesn't penetrate that far. By the time it filters through 100 kilometers of air, it's gone. The ultraviolet radiation behaves similarly. It spreads, weakens. At close range, it would strip ozone layers, damage DNA, disrupt photosynthesis. At 20 light-years, it contributes to atmospheric chemistry changes, but nothing catastrophic. The ozone layer thins slightly, recovers over decades. Gamma rays, if any made it out, would be even less concerning at this distance. They interact so strongly with matter that they barely travel through atmospheres at all. A planet with any atmospheric density effectively blocks them. Only objects without atmospheres, moons, asteroids, would receive the full gamma flux, and even then, the flux at 20 light-years is orders of magnitude weaker than at the source. There's a term for this, radiation dose. It's measured in grays or sieverts, depending on biological context. The dose a planet receives depends on the energy spectrum of the radiation, the distance and the duration of the exposure. For a supernova at 20 light-years, the total dose received over the months when the radiation is most intense is comparable to natural background radiation levels on Earth. Elevated, yes. Noticeable in sensitive instruments, but not lethal, not even particularly dangerous. 50 light-years out, the dose drops further. 100 light-years, and the supernova's radiation is indistinguishable from the general X-ray background of the galaxy. Still present technically, but lost in the noise. This is how danger fades. Not through active shielding, not through absorption by intervening matter, though that helps. Primarily through geometry. The radiation spreads across an expanding sphere, and the sphere's surface area grows faster than a human mind can easily visualize. Imagine holding a flashlight in the dark. Up close, the beam is bright, concentrated. Step back and the light spreads. The same total amount of light leaves the flashlight, but it's distributed over a larger area. Step back far enough and the light becomes indistinguishable from ambient illumination. The flashlight is still on, still emitting, but you can't see it anymore. Supernovae work the same way. The radiation continues outward for thousands of years. Photons traveling at light speed, carrying energy, moving through space. But with each light year traveled, the intensity drops. The danger diminishes. The lethal zone shrinks behind the expanding wavefront. There are complications, of course. Radiation doesn't travel through completely empty space. It encounters gas, dust, magnetic fields. High-energy photons sometimes collide with lower-energy photons, cosmic microwave background radiation, for instance, and those collisions can create particle-antiparticle pairs. Gamma rays interacting with the microwave background produce electrons and positrons. This saps energy from the gamma rays. They redshift, lose energy, arrive at distant locations even weaker than inverse square law alone would predict. Dust also absorbs radiation. Interstellar dust grains, microscopic particles of carbon and silicates, intercept ultraviolet and X-ray photons. The grains heat up, they re-radiate the energy as infrared. the high-energy radiation gets converted to low-energy thermal emission. This process, repeated across light years, transforms dangerous radiation into harmless heat distributed across vast volumes of space. By the time supernova radiation has travelled 100 light-years, almost all the high-energy photons have been absorbed, scattered or redshifted. What remains is a faint glow in infrared and radio wavelengths, still detectable with sensitive instruments, still carrying information about the explosion, but no longer capable of causing harm. Planets orbiting stars 100 light-years from a supernova would see the brightening in their sky, would detect the X-rays with telescopes, would measure the particle flux, but they would experience no biological effects, no atmospheric stripping, no ozone depletion. The supernova would be a spectacle, not a threat. This is different from the shockwave, which takes centuries to arrive and carries physical momentum. The radiation arrives first, within years or decades depending on distance, but it fades before it can cause damage. The shockwave arrives later, potentially more dangerous, but also slowed and cooled by that point. So the sequence is: light arrives, brightens the sky, fades over months. Radiation arrives, ionizes the upper atmosphere slightly, dissipates, then silence, decades of silence, centuries sometimes. And then, finally, the shockwave arrives, weakened, diluted, often too dispersed to matter. The danger diminishes at every stage. The radiation fades before arrival. The shockwave slows before arrival, and by the time either reaches a planet far enough away, they've both lost their teeth. Space dilutes violence. Patiently, inevitably, across distances too large to comprehend. The supernova screams into the void, and the void absorbs it, spreads it, turns it into something softer, something survivable, something that eventually becomes indistinguishable from the background hum of the galaxy itself. The gamma rays fade, the X-rays fade, the ultraviolet fades, and what reaches distant worlds is just light, just information, just the memory of something violent that happened far away and long ago. Binary stars are common. More than half the stars in the galaxy have companions orbiting each other in slow ellipses or tight spirals, bound by gravity into systems that can last billions of years. And when one of these stars goes supernova, the companion remains, still burning, still pulling material inward, and between the explosion and any planets orbiting the companion, there is mass. Mass blocks radiation. Not completely, but stellar material is dense enough and thick enough that high-energy photons cannot pass through unimpeded. They scatter, get absorbed, or re-emitted at lower energies, and by the time they navigate around the obstruction, they've lost intensity. The companion star casts a shadow, a cone-shaped region extending outward, where the supernova's direct radiation cannot reach, and if a planet happens to orbit within that cone, it experiences the explosion differently than it otherwise would. The brightening in the sky still happens. Light curves around the companion star, diffracted and scattered but still visible. The planet sees the supernova, dimmed but present. But the X-rays, the gamma rays, the hard ultraviolet that would ordinarily ionize atmospheres and damage organic molecules, those photons arrive in far smaller numbers, weakened by their detour through and around the companion's atmosphere and corona. This is not trivial. A planet that would have received a lethal dose of radiation might instead receive only a mild increase above background levels, the difference between atmospheric stripping and a temporary increase in auroral activity. The difference between extinction and survival. Geometry matters. the angle of the explosion, the position of the planet in its orbit at the moment the light arrives, the distance between the companion star and the planet. All of these factors combine to determine how much shadow the planet experiences. A planet directly behind the companion, perfectly aligned, receives maximum shielding. A planet slightly offset receives partial shielding. A planet on the far side of its orbit, facing the supernova with nothing between them, receives no shielding at all. Orbits move, planets don't stay in one place, so the shadow moves too, sweeping across the orbital plane as the planet continues its motion. And depending on orbital period and the duration of the supernova's peak radiation output, a planet might spend weeks in shadow or only hours. It depends. There are other sources of shadow. Dense molecular clouds, for instance, located between the supernova and a distant star system. The cloud absorbs radiation. Dust grains intercept photons. The far side of the cloud receives less radiation than the near side. Star systems behind the cloud experience the supernova through a filter. Its intensity reduced, its spectrum shifted toward longer wavelengths as the high-energy photons get absorbed and re-radiated as infrared. The cloud itself might be hundreds of light-years across. The shadow it casts extends even farther, a region of reduced flux stretching outward for kiloparsecs, and within that shadow, planets receive less radiation, less particle bombardment, less disruption. They still see the supernova. The light still reaches them, scattered and reddened, but present. But the danger is lessened, softened by the intervening material. Even the supernova itself can create asymmetry. Explosions are rarely perfectly spherical. The rotation of the star, the magnetic fields threading through its interior, the convective instabilities in the collapsing core, all of these introduce asymmetries into the explosion. Material gets ejected preferentially along certain axes. Radiation concentrates in jets or lobes. The supernova has a bright side and a dim side. A planet in the path of a jet experiences the full violence of the explosion, radiation and debris arriving with maximum intensity, but a planet offset by 90 degrees, perpendicular to the jet axis, experiences far less. The explosion is still visible, the light still arrives, but the most dangerous components, the hardest radiation, the fastest particles, miss entirely. They shoot off in other directions, spreading into regions of space where nothing happens to be present. This isn't luck exactly, though it resembles luck from the perspective of the planet. It's geometry. It's the fact that space is three-dimensional and explosions, even violent ones, are not omnidirectional. There are directions where the danger is concentrated and directions where it's sparse. Being in the sparse direction is survival. Humans studying exoplanets have started to consider this. When calculating habitable zones around stars, they account for stellar flares, cosmic ray flux, nearby supernovae. But they're also beginning to account for geometry. A planet's orbit, its inclination, the presence of companion stars or intervening dust clouds. These factors change the calculation. A planet that seems too close to a past supernova might have been shielded. A planet that seems far enough away might have been directly exposed. The shadow isn't permanent. Radiation spreads. Eventually it diffuses around obstacles, scatters off interstellar gas, fills in the regions that were initially dark. But eventually might mean centuries, millennia, long enough for a planet's atmosphere to recover from the initial insult. Long enough for ozone layers to rebuild, for atmospheric chemistry to stabilize, for life, if it exists, to adapt. There's also the debris, the physical material ejected by the supernova. It travels slower than light, takes centuries or millennia to arrive, and like the radiation, it can be blocked. A companion star in the path of the debris absorbs some of it, accretes it. The gas falls onto the star's surface, heats up, possibly triggers increased stellar activity. The planet orbiting behind the companion receives less debris than it would have otherwise. Not none. The debris spreads, fills in gaps, but the initial impact is reduced. Some planetary systems have multiple companions, triple star systems, quadruple systems. Each star casts its own shadow. The geometry becomes complex. A planet might be shielded from one direction but exposed from another, or shielded at one point in its orbit and exposed at another. The calculation requires tracking positions, velocities, timescales. But the principle remains simple. Mass blocks, distance dilutes, angle redirects, and if a planet happens to be positioned such that all three factors work in its favour, it survives in shadow, experiencing the supernova as a distant event rather than a catastrophe. Not all planets are so fortunate. Most aren't. Most experience the supernova directly without obstruction, and whether they survive depends on distance and atmospheric thickness and a dozen other factors. But some, those in shadow, those behind stars or clouds or positioned perpendicular to the explosion's axis, receive a reprieve, an accident of geometry that looks from the surface like providence. The shadow is not a guarantee. It doesn't make the supernova harmless, but it makes it survivable. It reduces the dose, spreads the danger thinner, gives the planet time to absorb the impact without collapsing, and when the debris finally arrives centuries later, it arrives weakened, slowed, dispersed. The planet's magnetic field deflects some of it. The atmosphere absorbs the rest. There's a period of increased meteor activity, auroras visible even during daylight. Atmospheric heating, but not stripping, not loss. The planet remains, altered perhaps, changed by the encounter, but intact, still orbiting, still capable of harbouring whatever it harboured before. The shadow saved it. Not through strength, not through resilience, just by being in the right place, by having something between itself and the violence, by the simple geometry of obstruction. The supernova explodes, the radiation spreads, the debris follows, and somewhere hidden behind mass, a world survives. The shockwave leaves the supernova moving at 15,000 kilometers per second, carrying the kinetic energy of several solar masses worth of gas accelerated outward in a fraction of a second, and in those first hours the wave is compact, dense, a shell perhaps a few billion kilometers across, which sounds vast but is nothing compared to what it will become, and the energy per unit volume is concentrated enough to vaporize anything solid, ionize anything gaseous, compress magnetic fields until they buckle and snap. 10 years pass. The wave has travelled about half a light year, roughly 5 trillion kilometers, and the radius of the expanding shell has grown proportionally, which means the surface area has increased by a factor of several thousand, and since the energy remains constant, energy doesn't disappear, it only redistributes. The energy per unit area has dropped by that same factor. The wave is still dangerous, still capable of stripping atmospheres, heating gas to millions of degrees, accelerating particles to relativistic speeds. But it's less concentrated. The punch has begun to spread. 100 years pass. The wave has crossed 5 light years. The shell radius is now immense, spanning 10 light years in diameter, and the surface area has grown to encompass a region of space large enough to contain thousands of solar systems. The energy flux at any given point on that surface has dropped by another factor of 100. What was once a wall of plasma capable of incinerating planets is now a hot wind, still moving at several thousand kilometers per second, but thin to the point where individual atoms are separated by meters, sometimes kilometers, and collisions between them become rare enough that the gas no longer behaves like a fluid, but more like a collection of independent particles moving in roughly the same direction. 1,000 years pass. The wave has reached 50 light-years, a distance encompassing hundreds of stars, and the shell has become so diffuse that calling it a shell feels misleading. It's more accurate to describe it as a disturbance in the interstellar medium, a region where the density and temperature are slightly elevated compared to the surrounding space, still expanding but no longer sharp, no longer distinct. The energy per unit area has dropped by another factor of 10,000. Planets in the path of this wave experience it as a gradual increase in cosmic ray flux, a warming of the upper atmosphere over decades, a brightening of auroras, but nothing catastrophic, nothing immediate. And by the time the wave has fully passed, which might take centuries given how slowly it moves relative to its size, the planet has had time to adjust, to respond, to redistribute the incoming energy without collapse. Time doesn't change the total energy. The supernova released a fixed amount. But time changes how that energy is distributed, how it's experienced, how much of it arrives at any given location in any given moment. Consider it this way. If you compress a year's worth of rain into a single hour, you get a flood, streets submerged, infrastructure overwhelmed. But if you spread that same amount of water across the entire year, you get weather, manageable, even beneficial, the same total volume but delivered at a rate that allows absorption, allows the ground to drink it in without drowning. The shockwave operates on a similar principle. The energy that would destroy if delivered all at once becomes survivable when stretched across centuries. A planet 50 light-years from a supernova doesn't experience the explosion as a singular event. It experiences it as a process, one that begins when the light arrives, intensifies gradually as radiation flux increases, peaks over a period of months as the supernova reaches maximum brightness, then fades over years as the light dims and then continues, much more slowly, as the shockwave finally arrives centuries later, delivering its energy not in a burst but in a sustained pressure that builds over decades, plateaus, then gradually diminishes as the wave passes and the density returns to background levels. The human mind struggles with this kind of causality, where the effect is separated from the cause by centuries, where the explosion happens in one era and the consequences unfold in another, long after anyone who saw the initial brightening has died, long after the event has passed from memory into history, and from history into geology, recorded only in ice cores or sediment layers or the isotopic composition of rocks that absorbed a brief pulse of cosmic rays during a period when the interstellar radiation environment was slightly elevated. There are species on Earth whose evolutionary timescales are short enough that significant adaptation could occur between the arrival of the light and the arrival of the shockwave. A bacterium with the 20-minute generation time could experience millions of generations in the centuries between. Entire populations could evolve resistance to increased radiation, could shift their biochemistry to accommodate slightly different atmospheric chemistry, could adapt to a world where the background flux of high-energy particles is 10% higher than it used to be, and by the time the shockwave arrives and the flux drops back to normal, those adaptations would already be embedded in the genome, carried forward into descendants who would never experience the conditions that shaped them. Time as buffer, time as dilution, time as the medium through which violence dissipates. The shockwave slows as it spreads, not just because it's sweeping up mass and radiating energy, but because time itself allows those processes to operate, allows the wave to interact with the interstellar medium over and over, millions of times, each interaction removing a small fraction of the wave's momentum, and the cumulative effect of those interactions Stretched over centuries is a deceleration that would be imperceptible on human timescales, but becomes significant when measured across the lifespan of the wave itself. A shockwave that started at 15,000 kilometers per second might be moving at 3,000 kilometers per second after 1,000 years, and at 500 kilometers per second after 10,000 years, and eventually after 100,000 years, it might be moving at the same speed as the general turbulent motion of the interstellar medium, indistinguishable from the background, no longer a wave but just gas, distributed, mixed, contributing its iron and oxygen and silicon to the next generation of molecular clouds that will someday collapse into new stars. Time erases the distinction between explosion and environment, not quickly, not obviously, but inevitably. The farther the wave travels, the more time passes, and the more time passes, the thinner the wave becomes, until eventually the only way to detect that a supernova occurred is to measure isotope ratios in distant gas clouds, looking for the signature of elements that could only have been created in a stellar explosion. Remnants so dispersed and so diluted that they're present in the concentrations of parts per billion, barely distinguishable from noise but still there, still carrying information about an event that happened 1,000,000 years ago and 10,000 light years away. Time stretches the wave thin, not as a metaphor, literally. The wave expands, the radius increases, the surface area grows, and the same amount of energy gets spread across a larger and larger region until the intensity at any given point drops below the threshold where it can cause harm, where it can even be noticed, where it registers as anything other than a slight statistical fluctuation in the ambient conditions of interstellar space. And in this way, time protects, not through active intervention, not through shielding or absorption, but simply by existing, by providing distance, by allowing the wave to spread, by giving the universe room to dilute violence into background. The supernova explodes, the wave expands, time passes, and what was once capable of destroying worlds becomes eventually just a gentle pressure, a faint warming, a barely detectable increase in particle flux that arrives so slowly, so gradually, that nothing notices and nothing needs to. The outer layers are gone. Hydrogen, helium, carbon, oxygen all ejected at thousands of kilometers per second, spreading outward into space. But at the center where the collapse began, something remains. A neutron star, 20 kilometers across, sometimes less. The mass of 1.5 suns compressed into a sphere small enough to fit inside a city. The density defies easy comparison. A teaspoon of neutron star material would weigh 1 billion tons. The nuclei are pressed so close together that individual atoms cease to exist. Electrons merge with protons. Neutrons dominate. The matter exists in a state that doesn't occur naturally anywhere else in the universe. You might expect the explosion to scatter everything, to leave nothing behind, but gravity doesn't allow that. During the collapse, the inner core reaches densities high enough that not even the pressure from degenerate neutrons can stop it from compacting further. It overshoots, bounces, and in that bounce most of the star's outer mass gets ejected. But the core itself, the innermost region where the collapse was most extreme, remains gravitationally bound. It doesn't expand, it doesn't disperse. It sits at the center of the expanding debris cloud and holds. The neutron star forms in less than a second. The temperature at formation is around 1 trillion Kelvin, hot enough that neutrinos flood outward, carrying away most of the energy. The star cools rapidly. Within minutes, the surface temperature drops to 1 billion Kelvin. Within days, it's down to 1 million. The interior remains hot for longer, insulated by the incredible density. But even there, the temperature falls over months and years as the star radiates energy into space. But cooling doesn't mean disappearing. The neutron star persists. It spins. Most neutron stars rotate rapidly, some completing hundreds of revolutions per second, a consequence of angular momentum conservation during the collapse. The original star was rotating slowly, but as it collapsed, the rotation sped up in the same way a figure skater spins faster when pulling their arms inward. The magnetic field also intensifies. The star's original magnetic field, already present before the collapse, gets compressed along with everything else. Magnetic flux is conserved. As the radius shrinks by a factor of 100,000, the field strength increases by a factor of 10 billion. The result is a magnetic field trillions of times stronger than Earth's, strong enough to affect the behavior of atoms, strong enough to shape the structure of space-time near the star's surface. This magnetic field doesn't vanish after the explosion. It persists, anchored in the neutron star's interior, threading outward into the surrounding space. Charged particles from the debris cloud spiral along the field lines. Some fall back onto the star, others get accelerated outward, creating jets and winds that extend for light years. You can see this in observations. The Crab Nebula has a pulsar at its center, a neutron star that emits beams of radiation from its magnetic poles, and as the star rotates, these beams sweep across space like a lighthouse. When the beam points toward Earth, telescopes detect a pulse, 30 times per second, regular as clockwork. This has been happening for nearly 1,000 years since the supernova that created it. The neutron star is not passive. It influences everything around it. The debris cloud doesn't expand symmetrically. Regions closer to the neutron star experience stronger gravitational pull. Material near the magnetic poles behaves differently than material near the equator. The star's rotation creates currents in the surrounding plasma. Magnetic field lines twist and reconnect, releasing bursts of energy that heat the debris and drive further expansion. Some of the ejected material never escapes at all. It reaches a maximum distance, slows under the neutron star's gravity, and falls back. This accretion happens slowly. Over thousands of years, a small fraction of the original debris returns to the star. The infalling material heats up as it approaches, reaching temperatures high enough to emit X-rays. Astronomers detect these X-ray sources and know that somewhere at the center, a neutron star is feeding. If the original star had a companion, a binary system where both stars were orbiting each other, the companion might still be there after the supernova. The explosion would have disrupted the orbit, possibly ejecting the companion entirely, but in many cases the companion remains, now orbiting a neutron star instead of a normal star. Over time, the neutron star's gravity pulls material from the companion's outer atmosphere. Gas spirals inward, forming an accretion disk around the neutron star. The disk heats, glows. Eventually, if enough mass accumulates, the neutron star might collapse further into a black hole. But even without a companion, the neutron star remains. It doesn't dissolve. It doesn't merge with the surrounding medium. Its gravity is strong enough, its density high enough that it exists as a distinct object indefinitely. Billions of years from now, long after the debris cloud has dispersed and mixed with the interstellar medium, the neutron star will still be there. Cooler, darker. No longer emitting detectable radiation, but present. A dense knot of matter sitting in space, invisible to most instruments, detectable only through its gravitational influence on nearby objects. There are old neutron stars scattered throughout the galaxy, formed in supernovae millions of years ago, no longer pulsing, no longer accreting, just inert objects 20 kilometers across, containing more mass than the sun, drifting through space at whatever velocity they were given when their parent star exploded. Some move slowly, some were kicked by asymmetries in the explosion and now travel at hundreds of kilometers per second, fast enough to escape the galaxy entirely over billions of years. These old neutron stars are difficult to study. They don't emit much light. They don't interact strongly with their surroundings, but they're there. Thousands of them, maybe tens of thousands. Remnants of supernovae so ancient that the original debris clouds have long since faded, but the cores remain, dense and dark, waiting. The neutron star is the part of the supernova that didn't leave. The part that couldn't leave, gravity held it, compressed it, turned it into something so dense that normal physics barely applies. The matter inside is in a state somewhere between atomic and degenerate. Neutron degeneracy pressure keeps it from collapsing further, but only barely. The star sits at the edge of stability, balanced between the inward pull of gravity and the outward push of quantum mechanics. If you could stand on the surface of a neutron star, though you couldn't, the gravity would crush you instantly. You would weigh billions of times more than you do on Earth. Light would bend noticeably around you. Time would run slower than it does in empty space. The horizon would curve upward in all directions, the surface so compact that you could see nearly halfway around the star just by looking forward. But you wouldn't stand there. Nothing stands there. The surface is smooth, featureless, a thin crust of iron nuclei, locked into a crystalline lattice by the intense pressure. Below that, layers of increasingly exotic matter. Neutron-rich nuclei, free neutrons, possibly quark matter in the very core, though no one knows for certain. The conditions are beyond anything humans can replicate or directly observe. The neutron star keeps what the supernova tried to scatter. It holds the core, the densest part, the part that collapsed furthest. And in holding it, the star creates a permanent marker, a gravitational anchor at the site of the explosion, a reminder that not everything can escape, that some things are too tightly bound to ever fully disperse. The debris cloud expands, the radiation fades, the shockwave slows and dissipates, but the neutron star remains, silent, dense, immovable, the part of the explosion that stayed behind. Ours shed mass before they die, not violently, not suddenly, just steadily, over millions of years. The outer layers, heated by fusion in the core, expand and cool. Some of the gas escapes, drifts outward. This is a stellar wind. Every massive star has one. The sun has one, though it's weak. A red supergiant has a strong wind, dense, fast, carrying away solar masses of material over the star's lifetime. This material doesn't vanish, it spreads into space, forms a shell. By the time the star's core collapses and the supernova begins, this shell is already there. Light years away sometimes. Still moving outward, though slowly now. The wind has cooled, the gas has thinned, but the mass remains, distributed in a rough sphere around the star, waiting. The supernova shockwave expands into this shell. At first, nothing unusual happens. The shockwave is moving much faster than the wind material. 15,000 kilometers per second versus a few hundred. The shockwave overtakes the shell easily, sweeps through it, heats it, compresses it, but then something changes. The shell is denser than the surrounding interstellar medium, not dramatically, but enough. When the shockwave passes through, it slows slightly. The dense material resists. The wave compresses the shell, and in compressing it, the wave loses energy. Not much, a small fraction, but enough to create a reflected wave, a reverse shock. The shockwave moving outward hits the dense shell and part of it bounces back. Not all of it. Most of the wave continues forward, but a fraction reflects, creating a secondary shockwave moving inward, back toward the center of the explosion. This reverse shock travels through the debris that's still expanding outward. The two waves, one moving out, one moving in, pass through each other. They interact. The reverse shock heats the debris again. Material that had already been shock heated once gets heated a second time. Temperatures rise. The gas emits more light. X-rays mostly. The emission is brighter than you'd expect from a simple expanding shell. Observers see this. They call it a double shock structure. The Crab Nebula shows this. So does Cassiopeia A. Both have reverse shocks visible in X-ray images, bright filaments where the inward moving wave is compressing material that's still trying to expand outward. The two motions create turbulence, instabilities, regions where the gas swirls and churns. This doesn't stop the expansion. The reverse shock isn't strong enough, but it complicates things. The debris doesn't move smoothly. It moves in layers, shells within shells, each one created by a different phase of the interaction between the expanding material and the surrounding medium. Massive stars sometimes shed multiple shells, not one wind, but several. Each phase of stellar evolution produces a different wind. The star expands into a red supergiant, sheds mass, then contracts, then expands again. Each time a new shell forms. By the time the star explodes, there might be 3 or 4 shells, each one separated by regions of lower density. The shock wave hits the first shell, reflects, continues, hits the second shell, reflects again. Each interaction creates another reverse shock. The result is a complex structure, multiple waves moving in different directions, forward shocks, reverse shocks, transmitted shocks that pass through the shells and continue outward. Humans modeling this use computers. The equations are too complex to solve by hand. You need simulations, hydrodynamics codes that track density, temperature, velocity across thousands of grid cells. The simulations show what happens. The shockwave fragments becomes layered. The smooth expansion you might imagine turns into something messier, more chaotic. But even chaos has patterns. The reverse shocks don't stop the debris. They slow it, they heat it, they create structure. But the outward momentum is too great. The mass ejected by the supernova is too large. The reverse shocks can't turn it around, they just disturb it, create ripples in the flow. And there's that. The reverse shock can compress material enough to trigger secondary processes. In some cases, the compression increases density to the point where gravitational instabilities develop. Dense clumps form. These clumps might eventually collapse on their own, forming stars or planets or just remaining as cold dark objects in the expanding nebula. The interaction between the shockwave and the stellar wind shells also affects where elements end up. Different elements were synthesized in different regions of the original star. Oxygen deeper in, like an even deeper. Iron at the core. When the star explodes, these elements get ejected in layers. The reverse shock mixes them. Turbulence disrupts the layering. Elements that should be separated end up mingled. This matters for the next generation of stars. When molecular clouds collapse to form new stars, they incorporate whatever elements are present in the gas. If the supernova debris is well mixed, the new stars will have a more uniform composition. If it's layered, some regions will be oxygen-rich, others iron-rich. The chemistry depends on the dynamics of the explosion, on whether reverse shocks formed, on how strong they were. There are supernovae where no reverse shock forms. The stellar wind was too weak, or too distant. The shockwave expands into near emptiness and just keeps going. No reflection, no layering, just smooth expansion, until the wave finally encounters the interstellar medium and slows. But in many cases, especially around massive stars, the reverse shock is present. It's part of the structure, part of the evolution. The explosion meets its own past and has to work through it, push against it, absorb its resistance. It's strange to think about. The star created the wind. The wind forms a shell. The star explodes. The explosion hits the shell pushes back. Not intentionally, just physically. Mass resists motion. Always. And in resisting, the shell changes what the explosion becomes, changes how the debris moves, changes where elements go, changes what survives and what dissipates. The blast reflects off itself, not completely, not cleanly, but enough to matter, enough to leave a mark in the structure of the remnant, enough that astronomers can look at old supernova remnants and reconstruct the history, see where the reverse shock formed, see how the debris responded. The explosion tries to escape its origin. Mostly it succeeds, but not entirely. Some of what it was stays behind. Some of what it created before it died comes back to meet it. And in that meeting, the explosion becomes more complicated, richer, layered with its own history. The shockwave continues outward, eventually, but it carries the echo of its reflection, the memory of encountering itself, and that memory is written into the structure of the debris, into the distribution of elements, into the patterns of light and density that persist for thousands of years after the initial explosion fades. The shockwave arrives carrying heat enough to ionize hydrogen, moving at velocities that should compress gas into collapse, delivering pressure that has triggered star formation in a dozen nearby clouds. But this cloud, this particular accumulation of molecular hydrogen and helium and trace carbon, scattered across 10 light-years, does not respond the way the others did. It absorbs the impact, accepts the energy, warms by a few degrees or a few dozen degrees depending on local density, and then continues existing much as it did before, which is to say cold, diffuse, gravitationally stable in a way that makes collapse unlikely over any timescale shorter than tens of millions of years. And the supernova energy, for all its violence and momentum, cannot change this fundamental equilibrium, because the cloud's internal structure, its temperature distribution, its turbulent velocity field, all conspire to resist the kind of compression that would lead to runaway gravitational collapse and eventual star formation. Temperature matters more than you might think when considering whether gas will collapse, because cold gas can radiate energy efficiently, which means that when you compress it, the heat generated by compression escapes quickly, allowing the gas to remain cool even as its density increases, and cool dense gas is more likely to collapse further under its own gravity. Whereas warm gas, when compressed, heats up faster than it can radiate that heat away, which creates internal pressure that resists further compression, stabilizing the cloud against collapse. This particular cloud sits at a temperature around 50 Kelvin, cold by terrestrial standards but warm by interstellar standards, warm enough that the hydrogen remains mostly molecular rather than atomic, which affects how efficiently it can cool, and when the shockwave hits and tries to compress it, the gas heats to perhaps 200 Kelvin in the densest regions, which is still cold, still well below the threshold where thermal pressure would dominate over gravitational attraction, but the heating is enough to increase the internal pressure just slightly, just enough to counteract the compression from the shockwave. The result is a cloud that settles into a new equilibrium rather than collapsing, absorbing the shockwave's energy by spreading it throughout its volume, distributing the heat across such a large region that the temperature increase per molecule remains small, negligible even, and over the following centuries the cloud radiates this excess heat away as infrared photons that escape into space, carrying the supernova's energy with them, dissipating it into the cosmic background, where it contributes nothing further to local dynamics. There is no drama in this process, no sudden transformation or visible consequence, just a slight warming followed by a slow return to the original state. And if you were observing this cloud with infrared telescopes, you might notice a brief increase in emission over a few hundred years, a temporary brightening that fades as the heat dissipates, leaving the cloud essentially unchanged. Neither compressed enough to form stars nor disrupted enough to disperse entirely, just existing as it has for millions of years with only a minor perturbation recorded in its thermal history. Stability is not the same as strength, though they can resemble each other from the outside, because the cloud is not resisting the shockwave through any active mechanism, not pushing back with internal forces or magnetic fields, but rather it is simply too dispersed, too spatially extended, too lacking in concentrated density for the shockwave to grab hold of and compress effectively, like trying to squeeze a fog, where the fog yields easily but never consolidates, never becomes dense enough to hold together under its own weight. Some clouds collapse because they were already on the edge, already marginally unstable, needing only a small push to tip them over into runaway gravitational contraction, and for those clouds a supernova shockwave is exactly the trigger required. But this cloud was never close to that edge, was never gravitationally bound tightly enough, and so the shockwave passes through and finds nothing to trigger, no instability to exploit, no critical threshold to cross. The turbulence within the cloud also plays a role, because the gas is not static but constantly moving, swirling in eddies and currents driven by previous disturbances, perhaps from earlier stellar winds or older supernovae long since faded, and this internal motion creates a kind of dynamical support where the kinetic energy of the turbulent gas provides additional pressure that resists compression, much like how stirring a pot keeps bubbles from settling. And when the shockwave adds energy to this system, it simply increases the turbulent velocity without fundamentally changing the cloud's structure. There are regions within the cloud where local density is slightly higher, small clumps that might have eventually collapsed given enough time, but even these clumps, when hit by the shockwave, warm just enough to stabilize, gaining thermal support that prevents them from continuing their slow inward drift. And so the potential seeds of star formation that existed in the cloud before the supernova passed through are neutralized rather than activated, left dormant, waiting for some other disturbance that might arrive millions of years from now, or might never arrive at all. Human beings studying star formation sometimes focus on the clouds that do collapse, the ones that light up with young stars and glow brightly in infrared and millimeter wavelengths, because those are the clouds where things happen, where change is visible, where the narrative is clear. But for every cloud that forms stars, there are many that do not, many that absorb shock waves and remain quiescent, many that exist in states of passive equilibrium where nothing triggers collapse and nothing forces dispersal, just a long, slow existence in the space between stars, accumulating cosmic rays and occasionally warming when disturbances pass through but never transforming into something fundamentally different. This cloud will eventually disperse, its internal turbulence gradually decaying over millions of years, the gas spreading thinner and thinner until it merges indistinguishably with the general interstellar medium, or it will be swept up by another passing shockwave in the distant future, one that finds it in a different state, perhaps colder or denser or positioned differently relative to nearby gravitational influences, and maybe that future encounter will trigger collapse, or maybe it won't, the outcome depending on conditions impossible to predict from the present configuration. But for now, in response to this supernova, this shockwave carrying the energy of a dying star across dozens of light years, the cloud does nothing. Or rather, it does the minimum required to absorb the disturbance without changing, warming briefly and then cooling, like a body of water that accepts a stone thrown into it, ripples spreading outward and then fading, the surface returning to stillness, the stone sinking into depths where it will rest undisturbed, forgotten, while above the water continues reflecting sky, as if nothing had ever interrupted its calm. The shock wave moves on, continuing its expansion into other regions where it will compress other clouds with different properties, some of which will collapse and form stars, and the energy it deposited here in this stable, unresponsive cloud will radiate away into the background, contributing to the universe's slow thermal equilibrium, and the cloud itself will remain cold and diffuse, a pocket of gas that refused to ignite not through resistance but through simple indifference, through being exactly what it is and nothing more. The supernova happened 10,000 years ago. The light arrived. It brightened skies across 1,000 star systems. Planets saw a new star appear, hold steady for months, then fade over years until it became just another dim point among millions. The radiation followed. X-rays ionized upper atmospheres. Cosmic rays increased, then decreased. The wave of high-energy photons passed through and left behind only slight chemical signatures. Ozone depletion that recovered. Isotope ratios that shifted imperceptibly. The shockwave came later, much later. Centuries after the light. It swept through molecular clouds, compressed some, heated others, triggered star formation in dense regions and merely warmed the diffuse ones. It encountered planets and either stripped their atmospheres or passed by to weaken to matter. It reflected off stellar wind shells, created reverse shocks, layered the debris into complex structures that glowed in infrared and radio wavelengths. And now, 10,000 years later, the remnant is fading. The debris has spread across 50 light-years. The density has dropped to near background levels. The temperature, once millions of Kelvin, has cooled to thousands. The shockwave velocity, once 15,000 kilometers per second, has slowed to a few hundred. The expansion continues, but it no longer looks like an explosion. It looks like drift. You can still detect it if you know where to look. Faint emission lines in optical spectra, radio observations showing slightly elevated densities, infrared maps revealing warm dust. But these signals are weak, fading. The remnant is dissolving into the interstellar medium, becoming part of the background rather than a distinct structure. The neutron star at the center still spins, still emits beams of radiation from its magnetic poles, but those beams no longer illuminate much. The surrounding gas has thinned. The pulsar sweeps across empty space mostly, its lighthouse beams finding nothing to light up. The heavy elements, iron, silicon, oxygen, carbon, have dispersed. Some have been incorporated into molecular clouds, some drift freely between stars. A few have already condensed onto dust grains, microscopic particles that will eventually become part of asteroids or planets in systems that haven't formed yet. The oxygen you breathe was made in a star. Some of it might have come from a supernova exactly like this one, an explosion so long ago that no record of it remains except in the atomic nuclei themselves, the signature of fusion and neutron capture preserved in isotopic abundances. The region where the supernova occurred is quiet now, not empty. Space is never truly empty, but quiet. The turbulence has settled. The magnetic fields have relaxed into smoother configurations. The gas has reached thermal equilibrium with its surroundings. If you didn't know to look for it, you wouldn't notice anything unusual about this patch of space. But it's different, subtly. The density is slightly higher here than in neighboring regions. The metallicity, the fraction of elements heavier than helium, is elevated. The dust grains are more abundant. These differences are small, a few percent, maybe 10% in the densest spots, but they matter. When the next molecular cloud forms in this region, it will have more heavy elements to work with. The planets that form around its stars will be richer in silicon and iron. The chemistry that develops on those planets will have access to elements that wouldn't have been there otherwise. The supernova didn't just destroy, it enriched. It left behind the building blocks for something new. 10 million years from now, this region might host a star-forming nebula. Young stars clustered together, surrounded by protoplanetary disks, the disks containing dust and gas and complex organic molecules. And buried in that dust, invisible but present, will be atoms from the supernova. Carbon and oxygen and nitrogen that once fused in a stellar core got ejected in an explosion, drifted through space for millions of years, and finally condensed into solid matter again. The cycle continues. Stars form from gas clouds. They fuse lighter elements into heavier ones. They explode or shed their outer layers. The heavy elements spread. New clouds form, new stars ignite. The universe gradually accumulates metals. That's what astronomers call anything heavier than helium, and with each generation the chemistry becomes more complex, more varied. The first stars in the universe had no metals at all, just hydrogen and helium from the Big Bang. They couldn't form rocky planets, couldn't produce the chemistry that leads to life. But they exploded, and their explosions seeded space with the first metals, and the second generation of stars had slightly more, and the third generation more still, and now, 13 billion years later, stars form with enough carbon and oxygen and iron to build Earth-like worlds, worlds with crusts and cores and atmospheres, worlds where chemistry can become biology if conditions align. Every supernova contributes. Not equally, not uniformly, but persistently. The explosions are violent, but the consequences are constructive. Destructive in the moment, creative over time. The silence after the last photon is not absence. It's integration. The supernova's energy has been absorbed. Its material has been distributed. Its influence has been woven into the structure of the galaxy. You can't point to a specific location and say, that's where the supernova happened anymore. The event has dispersed into everything around it. But the memory remains. In isotopes, in dust, in the slightly elevated density of gas that will someday collapse into new stars. The supernova didn't vanish, it transformed, became part of the medium it exploded into. And in that transformation, the violence becomes quiet. The destruction becomes potential. The end becomes a beginning that hasn't started yet, but will, eventually. When the conditions are right and the gas is dense enough and gravity takes hold, the silence is not empty, it's full. Full of what was and what will be, full of atoms that remember, in their structure, the furnace where they were made, full of space that remembers in its chemistry the explosion that passed through. The last photon faded years ago, centuries ago, but the supernova is still here, distributed, diffuse, waiting. Space remembers, quietly, patiently all. And when the next generation of stars ignites, they will carry that memory forward, burning with light that contains in trace amounts the remnants of stars that died long before they were born. If this helped you find some quiet tonight, consider liking or subscribing. It helps others discover these ideas when they need them. Thanks for listening. Rest well.